In this video, I want to show how the uncertainty principle is a simple result of waves, of the wave property of particles. So what I'm going to do is to actually derive in a simple way the uncertainty principle. Simple and not very rigorous way, but hopefully it will give an idea of what it really is about. Now, if you are watching this video for A-level or A-level physics, then this derivation would not be necessary. But you could watch it anyway for interest. Right. Now, what I've done in this case is I have actually written a simple computer program in which I generated a few different waves of slightly different wavelengths. That would be these 5 waves, 1, 2, 3, 4, 5. Now, if you look at them carefully, you'll see that the one at the top has the longest wavelength. The one at the bottom is slightly shorter. It will help if you follow this line. So if you follow this line, I've arranged the waves so that all the waves has a peak along this center line. But as you move away from the center, if you compare, say, the top wave with the bottom wave, you can see that by the time I reach, say, maybe this third line, the peaks are no longer aligned. Right? The peak there and the peak there is a bit off from this line, and it gets more and more off as we go further away. So the idea is that if I add these waves together, the place where all the peaks are at the same position would simply would add constructively, so that I get a big peak. Whereas as I move further away, the peaks are not together anymore, and at this position, for example, where the first peak is at the same place as the peak of the longest wavelength is at the same position as the trough of this shortest wavelength, with all the other wavelengths in between. We have a lot of destructive interference, and the peak gets smaller and smaller. And it gets smaller than at the center by the time we reach here. So what we can see here is that this is the result that I got by using my computer program to add up all these 5 waves, and this is the kind of result that I got, where I have a bigger amplitude near the center, and the amplitude sort of goes down. And the idea is that if we think of the amplitude of the wave as something that tells us that I'm more likely to have a particle there, and I'm less likely to have a particle there, then this shape of the wave means that the particle is more likely to be in this range. Alright, it's not likely to be further away because the amplitudes there and there are getting a lot smaller than at the center. Okay, now let me write down some symbols. Let's see. So let's say this wavelength is lambda 1. So that's my longest wavelength here, and lambda 2 is this shortest wavelength within this range. And the understanding here is that where I have the bigger amplitudes is where my particle is most likely to be. So that's my delta x. Okay, so by looking at this wave, I have the knowledge that my particle is within this range of the position. right? So for what I'm going to do, I need to relate these things to the uncertainty principle. Right? I need to know what is it that I'm trying to prove. Okay, so the uncertainty principle, let's remind ourselves, is that delta x, delta p is about equal to h, the Planck's constant. And the relation between p and wavelength, is given by the Broglie's relation, that the momentum p equals to Planck's constant divided by the wavelength. So, for example, in this case, I have lambda 1 and lambda 2. So, let's say the corresponding momenta are p1 for lambda 1 and p2 for lambda 2. That's p2. Now lambda 1 is the longest wavelength and lambda 2 the shortest. So if lambda 1 is the longest, then p1 must be the smallest. So this is the small one, that's the big one in this range. So the delta p there would refer to this range of p. Basically just p2 minus p1. That would be the delta p. Okay, so let's see if I can get this just by using this picture alone. Right? What I want to show is that given the Broglie's relation, of course, that is in a way a fundamental relation, so we can't derive that. And we are going to use this as our starting equation, or we're going to make use of this afterwards. For now, what I want to do is to see how we can arrive at this, okay, using the Broglie's relation and using just the waves alone. Okay, so let's see. Now, perhaps to give a hint of what is coming, and to maybe give to mention how I actually come up with what I'm going to say. So we're going to take a sneak preview at what I'm going to do, which is that we can actually rewrite this. Let me just rewrite this in terms of the wavelengths, lambda 1 and lambda 2. So as I was saying, delta p is p2 minus p1. So let me write this out in terms of lambda. So delta x times delta p, and delta p is p2 minus p1. Okay, so that would be, in terms of lambda, h over lambda 2, h over lambda 2 minus h over lambda 1. Okay, so I'm not deriving anything yet. I'm just rewriting the uncertainty relation in a way that's going to help me derive it afterwards. So I'm just rewriting the uncertainty relation. Okay, and you see that, notice that I have h, or the vector h, on both sides. Now if I divide both sides by h, this is what I'll get. I'll get delta x times 1 over lambda 2 minus 1 over lambda 1. So you see the h is gone. Oh, oops, equals 1. Yes, you see that the Planck's constant is gone. So it's as if if you think about the Planck's constant as kind of coming from the physics, as in the Broglie's relation, by stripping away the Planck's constant, we are left with basically just the wave, quantities that have to do with the waves itself, the x position, and the wavelengths. So it looks like this is something that we should be able to derive from just the wave properties. And indeed, we can. So that's what I'm going to do now. So coming back to these waves, let's see how we can arrive at this just by using this picture. Right, as I was saying, I'm going to take this as the x. Okay, I need to redraw this a little bit to make it more closer to what I'm trying to do. I'm going to say from this line to this line, I'm going to take that as my delta x. This line to this line. I'll take this as my delta x. Okay, now let's go back to this these 5 waves. As I was saying, that is the center, well, the place where I've chosen all the peaks to be at the same position so that they add constructively. Now, as I move away, now let's take a look at the next peak. If I follow this line, you see that the peak at this shortest wavelength is a little bit off. And if I look at the next line, this peak is off by a bit more compared to the longest wave. And the next one, it is off by so much that it's a trough here instead. Okay, so that's the place where we start getting more serious cancelling, destructive interference. And at this place, as I just pointed out, is where the longest and shortest waves are off by half a wavelength. Okay. Now, if I move the other way, these graphs are symmetrical. So down here, when I'm down here again, right, if I move from the center in the other direction by the same distance, I would again be in a situation where the 2 waves, the longest and the shortest wavelengths, are off by half a wavelength. So if I imagine, we might imagine that over this range, from there to there, over this, what I call delta x, it's a bit arbitrary, but I just let this be delta x so that I would get this answer. Okay, but this is a kind of a reasonable range. So if I go from there to there over this range of delta x, therefore the 2 waves, the longest and shortest wavelengths, waves would be off by a complete wavelength. Okay, let me say that again. From the center to here, this longest wavelength and the shortest wavelengths are off by half a wavelength. From center to the left, the longest and shortest waves are again off by half a wavelength. So if I go from here all the way to there, these 2 waves would be off by 1 wavelength. And in fact, you can count them. If you count from there, 1, 2, 3, 4, 5, 6. There's 6 wavelengths here. From there, 1, 2, 3, 4, 5, 6, 7, 8. Let me start again. 1, 2, 3, 4, 5, 6, 7. Sorry, 7. So there were 6 wavelengths there, and there are 7 wavelengths there, off by exactly 1 wavelength, as I've described. So now I'm going to just make it a little bit more general. In general, it doesn't have to be 6 and 7 wavelengths. It can be different number of wavelengths. But the idea is that by the time we move away from the center until they are off by half a wavelength, until the 2 extreme wavelengths are off by half a wavelength, there would be enough destructive interference for the center peak to come down considerably. Okay, so I'm just going to say that, let's say there are n wavelengths there over this range, over the range of over this range. Let's say there are let me introduce this color. There are n lambda 1 wavelengths from there to that. And down here, let's say there is, well, as we understand, there would be an additional wavelength, so it's n plus 1. N plus 1 times lambda 2. So an additional wavelength, because this lambda 2 is shorter than the lambda 1. Okay. Additional wavelength where the destructive interference become quite significant. Okay, and these two are equal. See, those two are equal. Okay, so let me write this out. So we have that delta delta x is equal to n lambda 1 from there. So that's the same as delta x. And we also have okay, we also have delta x is equal to n plus 1 lambda 2. N plus 1 lambda 2. Okay. Next time, what I'm going to do now, okay, if you look at this and you look at this, you might start to see some similarity. Okay, we have like all the relevant quantities here already, like delta x, lambda 1, lambda 2, delta x, lambda 1, lambda 2. Okay, so it could well be that if I do some rearranging here and with the extra n, so maybe we should eliminate the n, we might actually get this. So that's actually what I'm going to try and do. Okay. So I'm going to rearrange the two. Okay, rearrange the two. Now the first one, okay, it's going to give me delta x times, I'm going to divide both sides by lambda 1. 1 over lambda 1 is equal to n. The second one, I'm going to divide both sides by lambda 2. 1 over lambda 2, and that's n plus 1. Okay. Now, and I'm going to eliminate the n, so I will subtract that by that. Okay, I'm going to take this minus this. Alright. So delta x 1 over lambda 2, that 1 minus that 1. Delta x 1 over lambda 1. On the left hand side, and on the right hand side of n plus 1 minus n, which is 1. And it's now quite clear with delta x as the common factor that this equation would become this one if I factor out the x. Okay, and therefore I've derived it, alright, because from here all I need is to multiply both sides by h, I'll get this, and then I can invoke the Broglie's relation, and then I'll get h over lambda equals to the momentum, which is this. And this difference between the biggest and smallest momentum would be delta p, the uncertainty in momentum. Okay, so we have met here halfway, and if you look at the whole thing, you can see that just by looking at the waves, looking at a range of different wavelengths, we can go through all these steps and derive in the middle using the Broglie's relation. We can derive Heisenberg's uncertainty principle.